Hello everyone, this is Indradeep Kumar, Assistant Professor, IARE, Hyderabad. Today we will start the module 2, that is energy method. So in this video we will see about the strain energy method and strain energy due to axial load. So first let's see what is strain energy method. Right. So in module 1 what we had seen that elasticity method of structural analysis embodies the determination of stresses and or displacement by employing equation of equilibrium and compatibility in conjunction with the relevant force, displacement or stress-strain relationship. So in first unit what we had seen how stress will acting, because of that stress how displacements occur, or what at the this one the sum of horizontal forces equals to 0 for the equilibrium, sum of vertical forces must be equals to 0 for equilibrium, right? So these things are in a strain relationship. So these things we had seen in the first module. Now the application of that we will see in the second module. So the same way but in different method, right? We will find the same thing. So a powerful alternative but equally fundamental approach is the use of energy method. Means by using the energy method we can find the similar way what we did in the first module, but the way is different. These, while providing exact solution for many structural problems, find their greatest use in the rapid approximate solution of problems for which exact solution do not exist. So by which method that exact solution of those methods is not possible, by energy method we can also find the solution for that structural problem. Meaning what? Where those first module fails that to analyze, by this method we cannot just, you can say that analytical method or just formula like PL by E, there it fails. By using this method we can find that type of problems also. Okay, so means what? Energy method, by name itself is the energy method. So we will find here how much energy absorbed by that body, right? And because of that energy, why work done is what? Force into displacement. Once we have the energy, then we can just see. So work done is, or energy, simply you can say work done is force into displacement. What is energy? Form of work only. So this also can be F into D, either deflection, displacement or whatever. So once we know the energy, already we know that how much force is applying on that one. So with that we can find how much deflection is there. So let's see. Earlier we found by using the Hooke's law, right? Stress is directly proportional to a strain. From there that delta L by L we replace to the strain, and then we found the delta L. So instead of that, first find the energy stored by that body or member or beam, right? And then how much force is applied on that one, just divide those energy by the force, you will get the deflection because of that force. Okay. Next, also many structures which are statically indeterminate, that is they cannot be analyzed by the application of the equation of statical equilibrium alone, may be conveniently analyzed using an energy method. So those statically indeterminate structure that we cannot directly find by the equation of motion or by the equation of equilibrium, right? By using this method for that type of problem also we can find the solution. So means this is more effective than the analytical method. Now, energy method provide comparatively simple solution for deflection problem which are not readily solved by more elementary means. This, by using this we can solve for more elementary, that means not readily solved. Whatever the others are not giving, by energy method we will get that type of solution also. Energy methods are applicable to a wide range of structural problems and may even be used as indirect method of forming equation of equilibrium. So earlier from the equation of equilibrium we are solving, but now energy method is indirect way of forming that same equilibrium equation. So instead of directly like what sum of the vertical forces and sum of the horizontal forces equals to 0 for equilibrium, so instead of that, now in different way again we are finding the equation of equilibrium, because whatever is there that structure must be in equilibrium, then only we can use that one, otherwise we cannot. So we shall be concerned in this module with the solution of deflection problem and the analysis of a statically indeterminate structure. So in this module, what we will see about the deflection and about the that analysis of statically indeterminate structure. We shall also include some methods restricted to the solution of linear system, that is the unit load method, the principle of superposition, and the reciprocal theorem. So these methods we will use while solving the problems or deriving the formulas. Now, the strain energy and complementary energy. So let's see here. Figure A is actually in this slide. So figure A shows the structural member subjected to a steadily increased loading P. As the member extends, the load P does not work, and from the law of conservation of energy. So let's see here, this one, because once loading is there, right? So this structure has some weight. So because of their own weight, still some deflection will be there. That type is there. So first figure where when subjected to a steadily increasing load P. As the member extends, the load P does work and form the law of conservation of energy. So what happened here? As much as this P value will increase, that much more deflection. If suppose P value is less, then up to this only it will deflect, or this one deformation will be there. If more P, then up to this level. Then this P, even apply more P, then deflection will be like this. So depending upon how much load is acting or how much load you are increasing, according to that, the deflection will be there. And hence, once deflection is there, you are applying the load, means we are applying the load. So load means we are applying the force and displacement of the body is there, right? So means what? That will, we are doing some work. Where that work goes? Because of the law of conservation. Whatever work, neither energy neither be created nor be destroyed. So definitely what force we applied, because of that the energy produced, where that energy goes? That energy is stored in this part of the material, and that is called only the strain energy. So now once we have the energy, just as earlier discussed, once we have the energy, then we can find how much deflection will be there. If we know the force, if we know the deflection, then we can find the force. Rather, energy should be known, the stored energy in that one. Okay, just yeah, this work is stored in the member as strain energy. A typical load deflection curve for a member possessing non-linear elastic characteristics is shown in figure B. So in figure B, that is load versus deflection curve is shown. How? So let's see, the strain energy U produced by a load P and corresponding extension Y is given. So Y, when extension is there, so this is integration of 0 to Y, because the total extension is how much? Y. So from where? 0. So 0 to Y with integration. Which one is increasing? That by dy amount. That very small amount, it's increasing from 0 to 5. So integration of this, the value of this will give you the stored energy, that is the strain energy U. Right? Now just see here. So this is an arbitrary curve, right? Now here in this figure, whatever this curve is the elongation. So this part is the strain energy part, and this part is the complementary energy. It's obvious, strain complementary is what? Other to that one. So whatever the total energy is this one. So if this is strain, then the remaining part will be what? The complementary energy. So by complementary energy method also we can find same way. Just if this is a strain energy, this is complementary. This is total. So once we know the total, just remove the strain. We will get the complementary energy. By that also we can find. So here area OBD under the load deflection curve. So OBD is what? The strain energy, and OBA, this OBA, this part is what? Complementary energy. So this is subject stress, first one, the strain energy of a member subjected to simple tension. This is the figure 1. And here load deflection curve for a non-linear elastic member. So this is for non-linear, right? Just any random, because if linear is there, that curve should be straight. So it's a for non-linear member. This is the load versus deflection curve, where this delta y is a deflection along this, that is change in the length, and delta P is the by the amount the load is increasing or the small load acting on that beam or structure. Now, so now once that is the stored energy, then instead of U we can write same the complementary energy as C equals to 0 to P y dP. See the difference. If we will take this one, right? So area of this will be what? This into which one? Yeah, P dy. When dy is varying means if this along this if we are moving and keeping this constant, so along this is the strain energy. If we are keeping constant this part, that is why we are keeping constant and we are changing this part, so then we will get this part, then complementary energy. So the strain energy will be what? Keeping deflection constant, deflection variable, load constant. That will give you a strain energy. Complementary energy, keeping deflection constant and load variable will give you the complementary energy. So complementary energy as opposed to strain energy. So that is just opposite to that one. That's why we can also get that is exactly opposite to that one. Has no physical meaning, being purely a convenient mathematical quantity. So strain energy, there is no physical meaning that by okay this one. Once we have the strain energy, opposite of that one will be the strain energy. So we can once we have the complementary energy, we can find the strain energy. Once we have the strain energy, we can say. So there is no direct physical meaning for complementary energy. Once we have, we can utilize to find the strain energy. Once we have the strain energy, we can find the deflection of that one. However, it is possible to show that complementary energy obeys the law of conservation of energy, right? So complementary energy also obeys the law of energy, because whatever the type of energy is there, that must be conserved. The type of situation usually arising in engineering structure, so that its use as an energy method is valid. So means once we can find, then using a energy method is also valid. Now that is second equation, right? And this is the first equation, right? That I missed, so just here. So now differentiate both, right? So after differentiating, or let's see, here I'm differentiating this one. Okay, so just here or here, what we have, u equals to integration of 0 to y p dy, right? So I'm differentiating this with respect to, because y is varying here, so with respect to y, so du by dy equals to what? Differentiation and integration. Just let me write du by dy 0 to y p dy. So differentiation of this will get cancelled. What we will get? Du by dy equals to p, right? So differentiating this one. Now differentiate c. So see, this time p will be varying, so we will differentiate with respect to p. So c is what? Integration of 0 to p, and then here this is y into dp. After differentiating with respect to p, dc, or this differentiating with respect to p, so dc by dp will give you what? Similarly, after differentiating, this will be, so hence we will get here y. So see here, dy is p, and dc by dp is y, right? Now, okay, actually this is the first slide, that in second figure it should be b. Suppose that the curve of figure 5.1b, not 5.1b, it's b. The reference is given from here, just taken as a further reference. It's represented by the function, right? That. So where the coefficient function, this is here p b to the power n, that we'll see here again same, right? So where the coefficient b is the coefficient and exponent and r constant should be this b, and n is constant here. So this we are just taking a what curve function, right? Now with this we will derive. So let's, because just see here what we have, du by dy equals to p and dc by dp equals to y. So we have to, that means for finding this, just differentiate so that we can find the value of dp. Similarly dy, once we will have that, we will substitute in that equation. So let's first find dp. So differentiation of this one, so p is what, by to the power n. So b is constant, so we are differentiating this dp equals to keeping b constant, and formula of x to the power n is what, differentiation n x to the power n minus 1. The same way we will use here, x is y, so n into y to the power n minus 1, right? This is, and dp by dy here you can write, right? And now, so for dp equals to this y, cross multiply here, so this dp equals to b into ny to the power n minus 1 into y. So this will be the dp value. Now for finding dy, so dp, once we have dp we can substitute in previous slide equation, right? Now we have to find what, dy, so that we can replace dy. Okay, so now what we have, p equals to by to the power n. So from here what will be y, so first p by b equals to y power n. So now this n take this side, so this will be p by b power 1 by n equals to y. Okay, now differentiate this one. So what we are differentiating, we are subtracting the power, so I'm differentiating here. So first we are multiplying with this power, so 1 by n p by b to the power 1 by n minus 1, this is this one, and into, so this is equals to dy by dp. Now again same like this one, cross multiply, so 1 by n p by b power 1 by n minus 1 into dp. So let's see, we got this value for dy, this one for dp. Now we have dp dy, substitute in that equation. So now we have this one, u equals to 0 to p, 0 to y, p dy. Just now we found that value of, and that is in terms of complementary energy. Sorry, actually this should be here, it's got cross multiplied. So what we have, u equals to 0 to y, p dy. What we got, dy as 0 to y, right, p dy we got just here 1 by n, right, p by b, so into 1 by n p by b to the power 1 by n, right? So this is the dy, and into dp. Now for similarly c is 0 to p y dp. We found just dp here, dp is this one, so just put here, so 0 to p y dp is what, nb y power n minus 1 dy, nb y power n minus 1 dy. So this is constant, we can take out of the integration, then we can integrate y dy by 2. So after solving this, what you will get, du by dy as p, and hence du by dp is what, this value. This already we derived. So after substituting this, what is this one? That value is y. P by b power 1 by n is what? Y. So for this one, substituted for this part, substituted y. For this is 1 by n. So finally 1 by n y will have. Next, Igliana first theorem. Okay. So just see, this is the curve again. This is strain energy. This is complementary energy. right? So load deflection curve for a linearly elastic member. So this shows earlier we had seen for non-linear. That's why that was like this type of curve. And for that we found here this was the strain energy U and here it was the complementary energy C. Now that is for the what linear elastic material. So linear elastic member or linear elastic material, that curve will be a straight line as earlier discussed according to Hooke's law. So now this will be what? The strain energy. This will be complementary energy. So area of OBD will be the strain energy and OBA will be the complementary energy. So now from Castigliano theorems. So that is what this already we got. dC by dP equals to y and dC by dy equals to bn power y and y power n. Now n power, this one is what? B y power n already we assumed as n, sorry, p. So we assume that b y power n is p. So we can replace here. So now this becomes n p. Similarly, now after equating all the previous three equations, du by dy is equals to dc by dy equals to p, right? So once we will differentiate with respect to the deflection, either complementary energy or the strain energy, we are getting the same value. So just see, that's why it's there for that directly dc by dy. That means directly complementary energy have no significance. So we cannot physically that say, okay, with the strain energy, sorry, complementary energy is this much, so that much deflection will be there. No. By this, but here what we are proving, that complementary energy is equals to strain energy. So here dc by dy equals to y. That is equals to what? P. Means this and this is, that is complementary energy and the strain energy is equal. So once we have the complementary energy, we can say that is the strain energy, and based on that we can find. Similarly, once with respect to P we are finding, then what happened? Du by dP, that is also equals to dc by dP, which is equals to what? Y. Means another way also you can say, when complementary energy with respect to P we are finding, then the deflection is constant and we are getting the deflection. So we find by using the complementary energy method. Okay, and since complementary energy with respect to change in deflection or a small deflection or a small force, right, it's a coming same. So same we can use for the strain energy also, and hence we can say according to that we can find the amount of deflection because of the applied load. This equation, so these two equations, not one, these two equations is in the form of what is commonly known as Castigliano first theorem, in which the differential of the strain energy U of a structure with respect to a load is equated to the deflection of the load. So here you see, in which what? Differential of the strain energy of a structure with respect to load, right, is equated to deflection of the load here. So means du by dP is equals to y. That also is equals to dc by dP. Hence, now once we know this one, right, and then we can say this and this is equal. This dc by dP is equals to du by dP. Hence, du by dP is also equals to y. So now we can go with this one, complementary energy method, and then from the complementary energy method, once we'll have the complementary energy, we can say that complementary energy is equals to the strain energy, and with that we can find the deflection of that one. So now just recall once again. So first, the strain energy, whatever the deflection is there, according to that the stored energy in the body. Next, complementary energy. Complementary energy having no physical significance. If no physical significance, then why we are using that one? Nothing is. So for complementary energy, what we did? We proved complementary energy is equals to the strain energy with respect to either it's a deflection or a load. So in even either in terms of load, if you will take, that means if you will change the load, then also strain energy will be equals to the complementary energy. If we will change the deflection, or if deflection is different, then for the same complementary energy will be equals to the strain energy. So by varying both, that means by one, that complementary energy remains equals to the strain energy. Hence, we can find the complementary energy and then we can use as a strain energy, and then by that we can find the deflection or load acting on that member. Just recalling once again, so U is 0 to Y, P dy. Okay, so this is the strain energy formula. Let's see here, for strain energy, Y is variable, that deflection is variable. That is the difference is only for strain energy, deflection is variable. For complementary energy, load is, that applied load is variable and deflection is constant. Right. So from this curve only, this is the strain energy part, and the opposite to that one is the complementary energy. So now by this only we have to prove that complementary energy is equals to store, that is strain energy or not. If both are equal, then any one we can take, and by using that one we can prove. So instead of that one, first we will show that strain energy is equals to complementary energy, and if both are equal, then we will go with the complementary energy method and we can find our solution. Okay, so now this one, just I already explained these things. So again, just then C is what? 0 to P Y dP, right? So after from this one differentiated, then what we got? Du by dy equals to P, dC by dP equals to Y, right? So now these things we have. So if you will write like this, du, that is equals to P dy, right? So du, now integrate both sides. So from here, this is also you can say 0 to u, because earlier zero energy was there, because without deflection, once deflection starts, energy is stored, starts increasing up to what? Up to u. Similarly here, deflection is increasing from where initial deflection is 0 and suppose final deflection is y, then 0 to y. So after integrating this, integration of du is what? U. So u 0 to u, that is equals to p integration of 0 to y dy, right? So by this method we can find. So after this you will get u equals to p dy, sorry, p dy. Similarly for dc also from here, or simply just differentiate this one, then what you will get? dc by dp, dc by dp, that is equals to differentiation of dp with respect to dp y dp. So differentiation of this will be what? Simply y, because integration sign is there, differentiation and integration is just reciprocal, so it will get cancelled. So now there is no differentiation, so only dc by dp will give you y, and that is here. Okay, clear? After this, next what we did, right? Just assumed any function, that curve function, because already we had seen not for linear one, this is any for. So let's, this curve having function in terms of pressure is p b to the power, sorry, p equals to b to the power yn. So from now here, just we assumed, so for different curve it will be different depending upon the given equation. So from here, now we have to find what? dp and dy. So for finding dp, just differentiate simply this one, you will get what? nb y to the power n minus 1 dy. Similarly, for finding dy, first bring this b to this side. So this will be p by b equals to y to the power n. Okay, and then because we have to find the y value, so this becomes what? Y equals to p by b to the power 1 by n. Right, now just differentiate. So here this is y, differentiate, after differentiation we got this one, right? Now here, let's see, 1 by n, p by b, 1 by n minus 1 dp. Oh wait, now just see here, let's put here that value once again. Actually, that I said that is correct, not here. So P dy. So let's put P. Okay, dy value what we got here, that is correct, only 1 by n. So 1 by n P by B to the power, just see here, 1 by n minus 1. So 1 by n minus 1, okay, into dp. Right, now let's see here, P by B power 1 by, it's the P by B power 1 by n. So after substituting this here, you will get this one. Similarly, for this y dp, what we have dp here, and b y to the power n. So once we will multiply this one, this becomes y power n. So n b y power n, okay, dy, n b y power n dy. So that is correct, that is not wrong. Actually, I didn't simplify. So for this, just simply substitute the value of what, dy here and dp here. Okay, after solving this, what you will get, dy equals to p, and dp equals to 1 by n p by b power 1 by n. So what is p by b power 1 by n is nothing but it's a y. Hence that dy is p and dp is y by n, or you can say 1 by n into y. Now from those equation only the Castigliano theorem came, and according to that, this is for just linear elastic. What we derive, that is for non-linear also. For this linear elastic, so this is the linear, that is straight line curve, okay, and this is the strain energy, this is complementary energy. So from above those two equation, from here what we got, dc by dp equals to y. So dc by dy is bn y to the power n, that is equals to what, np, because this we assume that b y to the power n as 1. So when n is p, then this becomes equals to py, because n equals to 1 for the linear one, and we are considering that Castigliano theorem for the linear one. So for linear, power is 1 and power is, that's why n power. So now for linear we can say p equals to n b y only, simply because what we consider for this one, p equals to b to the power by to the power n, right? So for here this n will be equals to 1. So hence we can say directly that p equals to by. Okay, so for n equals to 1, this dc by dp will be equals to also p, and that is also equals to, already we had seen du by dy. Hence we can say du by dy is equals to dc by dy, which is equals to p. Similarly here we got dc by dp as y, and already we had seen du by dp also as y. So y by means, if dc by dp is y and du by dp is y, means definitely du by dp is also equals to dc by dp. And hence after proving this, okay, du by dp and dc by dp both are equal, that is equals to deflection, we can say if we will find dc by dp, that is complementary energy or strain energy, by finding both we can find the solution of the problem, right? So this is the reference. Most of the things what we are taken, that is from the TMAXN, but this also will help you to see and to structure the structural analysis, that means how to arrange these things. Okay, so this is the reference, you can refer these two, especially if you want to refer the book or related to content, then just go for the Maxen, that is Aircraft Structure of Engineering Student, either 4th edition. From 4th edition onwards you can even refer till 7th edition, it's available. So if you have any doubt, you can just complain on the video comments, or you can just directly contact me regarding the solution. In next class we will see the same in next method, by that means how the complementary energy we can, that how we can use the complementary energy, right? So in next video we will see what, the principle of stationary value of the local complementary energy, an application of deflection problem. So we will see how to use the complementary energy and then their application in deflection problem. So this we will see in next video. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.